Hello everyone, welcome to our low temperature thermochronology online class. We will continue the chapter 4, uranium, cerium, helium dating, thermochronology, analytical techniques. Today we will still focus on the second session about crystal characterization. The technique related to the backscattered electron image will be introduced this time. Firstly, some basics. In the scanning electron microscope, a number of different types of signals are produced as the electron beam interacts with the specimen. A large variety of electron beam specimen interactions are resulted from the collision of the beam electron with the electron or nucleus of the specimen atoms. These interactions can be divided into two general groups. One is inelastic scattering. It occurs when a beam electron interacts with the electric field of the electron of a specimen atom, resulting in a transfer of energy to the specimen atom. For example, the generation of secondary electron and characteristic X-ray. The other is elastic scattering. It occurs when a beam electron interacts with the electric field of the nucleus of a specimen atom, resulting in a change in the direction of the beam electron, without a significant change in the energy of the beam electron. For example, the generation of backscattered electron. For the different types of signals, the escape depths depend on the atomic number of the specimen and the energy of the electron beam. Generally, the escape depth of secondary electrons is approximately 5 to 50 nanometers. Backscattered electrons can escape from a depth 100 times greater. X-rays and chestoluminescence are able to escape from the whole of the beam penetration volume. For a better understanding of the information given by the backscattered electron image, our lecture will focus on secondary and backscattered electrons. In the scanning electron microscope, electrons used to image the specimen are classified according to their energy. A secondary electron is defined as an electron escaping the specimen surface with an energy of less than 50 electron volts. Secondary electrons are specimen electrons that obtain energy by inelastic interaction with beam electrons. They are predominantly produced by the interactions between energetic beam electrons and weakly bonded conduction band electrons or the valence electrons. The secondary electron coefficient is the ratio of the number of secondary electrons to the number of beam electrons incident on the sample. The coefficient is relatively insensitive to atomic number. For most elements, it is approximately 0.1. There is a general rise as the beam energy is decreased, primarily due to the reduction in interaction volume. When the specimen is tilted, and incident beam electrons travels greater distances in the region close to the surface. As a result, more secondary electrons are generated within the escape depths in these areas than in areas which are normal to the beam. Edges and ridges of the specimen emit more secondary electrons and thus appear brighter in the image, which is termed as the edge effect. Due to their low energy, only secondary electrons that originate within a few nanometers of the surface are able to escape and to be examined. Therefore, secondary electron is very sensitive to the surface structure. Secondary electron images give valuable information about specimens' topography, which are the most commonly used type in the scanning electron microscope. For the backscattered electron, it is defined as an electron escaping from the surface of the specimen with an energy of more than 50 electron volts. Backscattered electrons are produced by elastic interactions of beam electrons with nuclei of atoms in the specimen. The angle is such that the electron comes back out of the specimen. The backscattered electron coefficient is the ratio of the number of backscattered electrons to the number of beam electrons incident on the specimen. The coefficient increases with increasing atomic number. This relationship forms the basis of atomic number contrast in the backscattered electron images. The higher atomic number elements will appear brighter in the image. There's only a small change in the coefficient with accelerating voltage, less than 10% in the 5 to 50,000 electron volts range. Similar to that of the secondary electron, the coefficient increases with the tilt of the specimen. Backscattered electrons have relatively high energies, ranging from 50 electron volts up to the initial beam energy. They originate from much deeper within the specimen by elastic interactions. Since the emission intensity of backscattered electrons depends mainly on the atomic number, backscattered electron images can be used to detect contrast between areas with different chemical composition. Areas of the specimen composed of higher atomic number elements emit more backscatter signals and thus appear brighter in the image. For specimens containing various phases of different compositions, brightness in the backscatter electron image is thus a function of the mean atomic number, which may be calculated to a first approximation using the mass concentrations of the elements present. The backscattered electron image allows better characterization of zoning patterns of minerals. From the images, fine-scale oscillatory zoning of minerals is resolved better. A brief summary. Usually, secondary electron images are employed to show topographic contrast, and backscattered electron images are mostly used to show compositional variations. While for backscattered electron image, it may also contain topographic information, and the specimen should be well polished so that interference from topographic effects is minimal. That's the lecture today. Thank you for your attention.